like to introduce our keynote speaker, Dr. Mulvihill, who's the Executive Director for the Berkeley Center for Green Chemistry. So today, he's going to be sharing his passion and explaining to us about green chemistry. So please help me welcome Dr. Mulvihill to the stage.
Good afternoon, everyone. This is a real honor to be here and some really hard acts to follow. It's really wonderful work that all of the organizers are doing and that all of you are doing to try to advance greener, safer, better technologies in the world. I'm just going to talk for a few minutes and hopefully I'll get some input and participation from you about my favorite topic, which is molecules. I'm a chemist and I love molecules. Does anyone have a favorite molecule out there? I have mine up here. One of my favorite molecules. Anyone know what it is? Yeah, do you have a favorite molecule? What?
Coffee molecules?
So coffee, why do you think people drink coffee? What's in it? Caffeine. So that's the molecular structure for caffeine. Where else is caffeine? Sodas, tea. Over 90% of people or adults in the US have some sort of coffee in their diet or some sort of caffeine in their diet. Why is that? What do you think it does? Because we're tired. That's right. It keeps us from getting tired because it blocks the adenosine receptor in our bodies. That's the receptor that actually triggers our body to become tired. It also increases our body's ability to attract dopamine and produce dopamine, which makes us feel happy. So that's why you put these things in beverages or we drink coffee and tea. And it's an example of the way that molecules in our daily life cause an effect. I mean, this is one that I tend to like. It's personal choice. But there's molecules all around us. So did it change? I'll just go over here. Where are some places that you find molecules? Water. Water is a molecule. Everywhere. That's right. And so if there's molecules, like caffeine, it's naturally occurring, there's molecules everywhere, all around us. There's molecules that are in our homes, that are in our environment, that are in the air. There's molecules everywhere. What are the differences between the sort of molecules that make up plants, that make up our consumer products, and that make up our electronics? Tell me about the molecules in each of these things. Yeah?
Molecules that are in plants are organic. They originally come from, they're not man-made.
They're organic. They're not man-made. They come from nature. What do you think they're made out of? What sort of atoms are in those molecules? What's that? Cells. So they're made inside cells. Molecules are even smaller than cells. They're made out of atoms. Ones that are in plants often have things like carbon and hydrogen and oxygen. So we heard about CO2 and the production of oxygen. Things like sugar and cellulose. The things that make up plants are often carbon, hydrogen, and oxygen. Where do you think the molecules that go into consumer products come from? Plants. Sometimes they come from plants. Where else can they come from? A factory. And where did the molecules come from before they got to the factory? Petrochemicals. They often come out of the ground. So a lot of the stuff are plastics. A lot of the things that you'd find in consumer products, they come from the petroleum industry. They're a derivative of things that we pull out of the ground. It's part of that carbon cycle. How about the things that are in our electronics? Where do those come from? Yeah? Atoms. They're made of atoms. Where do those atoms come from? Rocks. That's right. They come from minerals. They come from rocks and mining and other things that we pull out of the earth. So molecules are all around us. And depending on what we're making, we get to them in different ways. So nature makes its molecules using something called the carbon cycle. We already heard about the carbon cycle today. I'm really excited. When we were talking about global warming, we're focusing on the way that we burn fuels, and that creates more carbon dioxide. That carbon dioxide creates all of the input chemicals, whether it's cellulose or proteins or other things that plants are made out of. Chemists, on the other hand, we do our chemistry by taking those raw materials, often raw materials of the petrochemical industry, but increasingly with green chemistry technology, we're taking things that come from plants, and we go into the lab and we also combine them into the useful things that we use every day. So one of the things that I like to teach and that I like to do as a green chemist is think about how does nature take matter and move it through its cycles, and how can we emulate that? Because what I really want to see in the future world is a place where, like nature, we have circular design. So we understand where our molecules come from. We may still combine them in new and exciting ways, but that we make sure at the end of life they get used or reused in a responsible way. So that's what gets us to green chemistry and the 12 principles of green chemistry. As a chemist, what we mostly do is we take materials, we combine them in reactions, and those reactions make products. So what I want to show you now is I bet you already know what green chemistry is. Before I even put up the 12 principles, if you didn't already hear about them downstairs, I bet you already know what green chemistry is. So what sort of materials, if you wanted to make greener, safer, more efficient chemistry, what sort of materials would you use to start with in green chemistry? Would you want products for window washing? And what sort of things would you want to be in your window washing thing? Would they be safe or dangerous? So you'd use safe things. What other sorts of things would you use? Non-toxic chemicals. So you'd start with non-toxic chemicals. What other sort of things would you start with? Organic materials, things that potentially come from the environment, come from biomass. Absolutely. What do you think? Natural things, things that are going to be naturally replenished over time. Absolutely. So what sort of reactions would you want to do? Would you want to have your reactions take a lot of energy or a little bit of energy? Little bit of energy. You want your reactions to be efficient. What did you have to add? What's that? Just a little bit of energy. That's right. And the products that we make, what do you think the products of green chemistry should be like? Yep. Biodegradable. At their end of life, they should turn into things that disappear. How about you?
Safe for the environment?
Safe for the environment. Absolutely. What type of products? That's right. The things that we make shouldn't be harmful. They should be safe at their end of life. So when you think about it, what we just came up with are the underlying principles of what it would take to do green chemistry. We would start with things that are biorenewable. We'd minimize the use of things that are harmful. We would do things in a way that creates the least amount of waste. These 12 principles were originally written down in this book by John Warner and Paul Anastas back in 1998. This really started as a collaboration between industry and the EPA. So Paul Anastas was at the EPA. At this time, John Warner was at Kodak. And the whole idea was, if you have a new innovation, just like we heard about and I saw earlier today, if you had a new idea, and a new idea that was actually done in a safer way, how could you get the EPA to accept this new idea as being something that was better and easier to get through the regulatory process? And in the process of thinking about what they would give an advantage to and how they would give that advantage, John Warner and Paul Anastas came up with these 12 principles of green chemistry, which have since then been used to guide the work that myself and many other chemists around the world do at the bench. Like we already said, it's important to consider when you're at the bench and when you're making a new product, no matter what sort of product it is, that you actually have to get things from our environment, whether you're extracting them from oil or getting them from plants. We have to transform them And then during their use, they have to do their productive function. It's really important that whatever you're doing is providing a productive function. And then at the end, we want to make sure that things are safe, that they biodegrade, that they can be reused, that they're not going to be long-term on this earth. So I want to tell you 2 examples of work that students of mine have done that exemplify these 12 principles of green chemistry. Because what chemists do on a daily basis, do any of you want to become chemists when you grow up? I like to see that, at least a few hands. Excellent. What chemists do on a daily basis is we make stuff. We mix things together, we make stuff, we measure those chemicals to make sure we understand what we made and how we made it, and we also teach others. So I'll give you an example of 2 projects. The first one talks about ways of dyeing fabric, and the second one talks about building materials that show how the 12 principles of green chemistry can be put to use to actually make new stuff, including stuff right here. So the first one, it comes from dyeing and the dyeing industry. So the clothes we wear, they go through a lot of processes before they get to our closet, right? So the cotton or the other fibers, whether they come from petroleum or natural sources like cotton, have to be grown or produced. And then in order to get all the colors that you see in the room, they have to be processed. They have to be dyed. Dyeing is actually a very energy and water and chemical intensive process. In order to dye chemicals, what you're basically trying to do is take a large molecule, usually something derived from petroleum, BASF, the largest chemical company in the world. They started off by making dyes. They started off by making dyes that were derivatives of the coal industry, as a matter of fact. And those original dyes, they're hard to get into fabric, actually. They're very large. So in order to get them into the fabric weave, you have to heat it up in water using a lot of energy. And then after you've dyed the fabric, what you often do is just put that water into the environment. So you can see here red dyes and blue dyes being emitted outside of textile plants. And the problem is these dyes, although once they're on our fabric, they're pretty safe, they're not safe for the environment. They're not safe for those aquatic ecosystems where they're being released. So my challenge to my students and to myself was how could we do this process, create color in fabric, without using a lot of energy and without creating a lot of water or waste that we'd emit to the environment. So one of the first things we do is we say, well, how does nature do this? Are plants colored? Yeah. So why are plants colored? Yep. There's chlorophyll, absolutely. That's why the leaves are green. And where does that come from? Where do the chemicals come from that make chlorophyll? A hint, I've already talked about it. What's that? Yep. The sun provides the energy to turn CO2, the carbon cycle, into large molecules like the ones that are on this slide. So these are actually molecules that, like every other molecule in a tree, are made through the carbon cycle that go into making the brown color in bark, because this is actually lignin in this case. Chlorophyll is another thing that causes colors in plants. Anthocyanins are another thing that causes color in things like flowers and seeds. So you have lots of different molecules that all come from small building blocks, and plants build up those large molecules from small building blocks as they need them. What if we could do the same thing? What my students did and what we did in lab was say, we know that there are natural dyes. We know that it's possible to use small molecules and turn them into large, colorful molecules. So what we did was we started with food-grade chemicals, things that were safe to eat, that were made out of those same building blocks, things like vanillin, cinnamaldehyde, things that are basic building blocks of plants that aren't colored. So this was the real interesting thing. It wasn't colored. They were much smaller, so they're much easier to get into the fabric. And then we can apply a little bit of heat and no additional water and actually create colored pieces of fabric. So it was a way to build the dye inside the fabric rather than creating and trying to put a dye from outside the fabric inside. So this isn't on commercial scale yet. we're still in the laboratory, but if things on the laboratory scale were to work on the same scale as the current industrial scale, you can see that it would take a lot less water. Instead of 80 liters of water per kilogram of cotton, our process would take something like 1 liter of water per kilogram of cotton. Instead of using a lot of energy to heat all that water, we use a little bit of energy just to heat the fabric. Right? It's not zero impact. One of the important things I want to show here is that my process isn't zero impact. It's just a lot less than the current industrial process. How did we do that? We did that by looking at how nature worked, how nature makes color by taking small, safe, and abundant molecules, and as it needs it, turning it into the large, colorful molecules that we see in the environment. So the next story is actually about building materials. It's about this stuff right here. So there it is on a roof. Here it is, and you can pass it around, and I'll explain what they are as you pass it around. That stuff is actually made out of waste. It's made out of waste from the paper processing industry. It's made out of waste from the cardboard industry. It takes waste sources of cellulose. So things that you put into those blue recycling bins, so to speak. And it says, how can we put it together in a way that can create a building material, that can be strong, that can be resilient, and that can be safe? What's really important is we want to make sure we can do it without using any harmful chemicals. So we want to start from a waste product. We want to turn it into something that's useful. So what you see here is one of our undergraduate students at UC Berkeley actually standing on top of a panel made just like that, made out of waste cardboard. And he made it by taking natural binder, something that was made out of protein and made out of starch, binding it together using pressure. That's what the press on your left is. And it works really well. And in fact, the first of the two things that I'm passing around, the thing that isn't orange, the one that's not coated, it's that material. You can feel that it's a strong material. But on its own, you could never use it in a building. Why do you think you might not be able to use a building made out of starch and natural materials in a building? Any guesses what will happen? Oh, if you punched it, it would be fine. It's really strong, but that's a good idea. What else might happen to it in the environment? Melt. What would cause it to melt? Water. That's right. So one of the problems with using these natural materials, if you've ever gotten a piece of paper wet or cardboard wet, you can tell that it's not as strong anymore, right? And so the traditional ways of making things waterproof are often toxic and using petroleum resources. My challenge to the students was, how could you create something that would allow you to use safe and natural coating products rather than potentially harmful ones, and make a resilient material? So one of the things that I'm passing around there as well is a small square block that you see has a cut in it. A cut like you'd often find on a building material. You either cut it because you put a nail in your wall, or it gets scratched because it's on the roof. And what's important is you don't want it to swell. You don't want it to become weak. So we were trying to make an additive using green chemistry, so things that were natural and safe, that we could add to this already renewable and useful material so that it could be used outdoors. So we needed it to be water resistant. We wanted it to be biodegradable. We wanted it to be environmentally friendly. It needed to be low cost, and it needed to be made out of available resources. So one of the things that we found that worked is actually something you've probably all consumed, which is nice because it means it's safe. So calcium stearate is actually a drying agent that you find in a lot of candies like Smarties and Neckos, those sort of things. You can actually add that to these panels, and what happens is it creates a hydrophobic surface. It makes it so the water doesn't want to go in, and if the water doesn't want to go in, the material stays strong. One of the things that means is instead of water going all the way through like you see in the control, so this is a panel that's swelled and gotten wet and was easy to break, it stops. So the outside gets wet, just like a normal piece of wood would, but it doesn't seep all the way through into the actual material. So the material is able to retain its strength, retain its usefulness, but without using potentially harmful coatings. So those are my 2 examples of some of the work that we're doing at UC Berkeley to incorporate those 12 principles of green chemistry. And I'm glad to hear that some of the folks in the audience are considering becoming chemists, because I think chemistry is awesome, and I think molecules are awesome. But even for those of you who just want to interact with materials on a daily basis, because no one can get completely away from chemistry, I want to end my talk by talking a little bit about how does green chemistry and the principles of green chemistry apply to our everyday life. Any guesses? What are the sorts of things you can do, even if you're not making new materials, that are like the principles of green chemistry? How can you apply the principles of green chemistry in your daily life? Yep. Recycling, that's a great way to do it. Reuses resources. Yeah. Buy organic food, try to buy things that don't have additional or not useful or harmful chemicals on them. Absolutely. Other ideas?
Wash your laundry with soap nuts.
Wash your laundry with soap nuts?
Soap nuts.
What are soap nuts?
Soap nuts are these nuts that come from Australia, and the inside lining of the nuts is, what do you call it? It's whatever soap is.
It's a surfactant.
It's a surfactant.
Wow.
And so when you shake it up in the water, it becomes like soap, but then it's completely biodegradable and there's no plastic involved.
So it uses biodegradable things. It comes from renewable resources. It also reminds me of something that is native to California. The California buckeye creates those surfactants, and they were actually used by Native Californian people to capture fish. You'd put you'd put these in water, and it would create surfactants that would coat the gills, and they would float to the surface. So soap nuts may have other purposes as well. But yeah, that's a great example. Other ideas? Reuse objects, absolutely. That way, at their end of life, they continue to do useful things. Do you have one back there? Color your own clothes. I love it. That's a great idea. You could definitely color your own clothes with safe colorants after you ask your parents. Yep. Grow food in your garden, absolutely. Take advantage of that carbon cycle right in your own backyard. Those are all great ideas, and I promise they're just as good as any of the 6 that I'm going to show you, but I'm going to give you a couple of themes that I like to think about in my daily life as well as my work. So the first is really buy and use only what you need, and there's 2 examples of this. There's really what we're talking about here in terms of conservation and not using additional resources. There's also specific things that I look for, and I'll tell you about those. Reusable and recyclable things, that already came up. Choosing greener and safer products, that already came up. Preventing accidents is also a really important thing, so using things as they were intended. And staying informed, and that's what events like this and community like this is really all about. So I really think that you're already practicing green chemistry in your daily lives. So one thing that I look for as a chemist is I love reading labels. And there's some things that I look for on labels that I really don't like to see. So this is just one example. So I don't like using additional chemicals that aren't needed. Triclosan is one of these chemicals that ends up staying around in the environment. It is potentially harmful for human health. It is definitely harmful for environmental health. And it's a molecule that, for most of these products, doesn't actually perform any additional use. So this is a great story of how chemistry and society and marketing all come together. Back in the 80s, there was a big scare around AIDS, which is caused by a virus. And so you saw a proliferation of soap, Dial in particular, but many soap companies starting to market antibacterial soap. One, that's not going to help you stop AIDS because AIDS is a virus anyway, but it captured the fear of the time. And so you started getting consumer product companies competing to make antibacterial soap, which in some ways is laughable because soap is antibacterial. That's why we use it in the first place. We actually use it because it breaks apart the membranes of microorganisms and kills bacteria. That's why we wash our hands with soap. So some of these personal care products that have triclosan in them, it turns out that the triclosan doesn't do any additional killing of bacteria. So it was put on there to support a marketing claim that doesn't actually make the product any better. So this is a molecular example, and there are others of things that aren't necessary but that were put in there to capture the fear of the time. So this is one that I personally look out for. Other people look out for flame retardants that are unnecessary and no longer needed. In fact, the state of California now lets you buy furniture without flame retardants in it. And it turns out ever since folks stopped smoking at home, fire deaths have reduced greatly, much more so than the use of flame retardants. So there's many ways to solve this problem. So those are some chemical examples of what I mean by when I say only buy and use what you need. This already came up, right? Composting and separating waste. Most of you are already doing it. I was already seeing it going on here. Here's a couple of things that you can look out for when you are trying to buy greener products. One is the app called The Good Guide that allows you to look at what some of the chemistry is inside it. There are also a number of rating systems that allow you to see if it's a cradle-to-cradle or a green chemistry sort of chemical inside. And lastly, it's the staying informed piece that I think is so important. And that's why it's a real pleasure to be here. And there are many other resources. We have resources on the Berkeley Center for Green Chemistry. But resources like this conference are a great place to find more information about what it takes to be a green chemist. And anytime I give a talk in public, it's really important for me to say this last thing, which is I don't want everyone to run out and throw away all their consumer products and buy brand new ones. I don't want everyone to jump on the next biggest bandwagon because really it's an incremental process. Just like improving a building material or making a new fabric dye takes a long time, when it comes to the stuff that you bring into your home, just use what works. Try not to throw as much stuff away. And when you do have to buy something new, then look for the things that tend to be greener and safer. I think that this was one that got me. I was worried about Teflon on pans, and then I realized I could just use, it was much cheaper and readily available. I could get it at the local flea market, cast iron pans. They're just stainless steel, and if anything comes off, it's actually iron into your food, so you don't have to worry about it. So new innovations aren't always the answer. Sometimes it's actually the old stuff that works just fine. That's one of the things that I definitely learned in the course of studying a lot of new chemistries. So with that, I'm happy to answer any questions, or if I'm allowed to. Otherwise, I hope you had a wonderful time here at this conference, and thank you again to the organizers and all of you for being here.
Goodbye.